So, we have discussed in our first lecture what is system of equations, linear equations. We have also seen your equivalent systems, and we have also seen while discussing as a special case that solution of system equations as a linear combinations of the some column vector form type, that is also we have seen in terms of as a geometrically also in terms of equation of line or planes. So, these things indicates that one has to proceed in a particular path to answer the question whether a system of equation of m equations in unknowns have solution or not, and if at all it has solution, how to find. So, we need to represent that system of equations in terms of matrix form. If you recall, we wrote the first system of m equation in unknowns, like a11 x1 plus a12 x2 plus a1n xn equal to y1, a21 x1 plus a22 x2 plus a2n xn equal to y2, am1 x1 plus am2 x2 plus amn xn equal to ym, where aij belongs to capital F for 1 less than equal to I less than equal to m, 1 less than equal to j less than equal to n. And of course, yi belongs to capital F, okay, for again 1 less than equal to I less than equal to m. So, this one I wrote as a system of m equation in n unknown. I will give the name as star please. Now, this system of equations can be written in a compact form like by introducing an m cross n matrix, say A x equal to your capital Y, where capital A is equal to aij, that is m cross n matrix over capital F, and capital X is basically x1, x2, xn transpose n cross 1 column matrix, 1 column matrix over capital F, and capital Y is equal to y1, y2, ym transpose this m cross 1 column matrix over this one place. Okay. So, I can write down this star in a very compact form Ax equal to y, it is matrix form place, and again then say that y equal to 0 is my homogeneous systems and otherwise it is a non-homogeneous system place. We have discussed in our first class that to check whether system has solution or not, one has to follow elimination procedure please. While doing the elimination procedures, one has to do basically 3 basic elementary row operations. So, I will do this elementary operation in terms of row or in terms of column please. So, to check whether system has solution or not, we will consider the elementary row operation please. So, there are 3 basic elementary row operation please. Elementary row operations. The first one, multiplication. This elementary row operation I will talk in terms of only matrix A, even though I can do it for both sides. I mean, in the system A x equal to y, elementary operation for A as well as y, but I will do it for sake of simplicity for A only. And the concept will be can be extended easily for the y also. So, multiplication of rth row of A by a non-zero constant, zero constant C. So, this is one elementary row operations. Mathematically, that is in function form, I can write down E of Aij equal to as Aij if I not equal to R and 1 less than equal to I less than equal to M, 1 less than equal to J less than equal to N place. And in the case of I equal to R, it is basically C times A R J if I equal to R. So, this is the first elementary operations. Then the next one I am saying that replacing rth row of A by C times sth row of A plus rth row. So, mathematically it is basically E of Aij equal to, I can write down Aij if I not equal to R and 1 less than equal to I less than equal to M, 1 less than equal to J less than equal to N, and this is A Rj plus C times Asj if I equal to R and this one. Certainly S will lie in between 1 to M please. The third one, exchange of rth row by sth row of A. Now, these elementary operations again can be write in functional form. It is like this: E of Aij equal to Aij if I not equal to R and I not equal to S, 1 less than equal to J less than equal to N, and this is equal to Asj if I equal to R and 1 less than equal to J less than equal to N. This is Arj if I equal to S. So, this is my third elementary row operations. The total elementary operation is nothing, I can say is some sort of combinations of these three elementary row operations please. Interestingly, each elementary row operation is invertible and introduce an invertible matrix called as elementary matrix. Elementary matrix space. For examples, system is A11 x1 plus A12 x2 plus A13 x3 plus A14 x4 equal to say 0. I have taken homogeneous case, but this can be done for the non-homogeneous case also. And A21 x1 plus A22 x2 plus A23 x3 plus A24 x4 equal to 0, and A31 x1 plus A32 x2 plus A33 x3 plus A34 x4 equal to 0. This goes to, I can say Ax equal to 0, where A is a 3 cross 4 matrix and X is a 4 cross 1 column matrix space. Multiplying second equation by 0 not equal to C. So, in this case we will have new system say Bx equal to 0, where the first row of B is the first row of A, third row of B is also third row of A, but the second row of B is a C times second row of A. Now, this one I can write down, if I multiply by 1 by C to the second equation of the Bx equal to 0, certainly I will get back to my first system Ax equal to 0. So, here see, to obtain B, I have introduced an elementary matrix say E1, which is equal to like this 1 0 0 0 C 0 0 0 1. Here E1 into A equal to B, you can immediately check this is true. Now, if I consider E2, E2 is another matrix, I mean which I have obtained by multiplying second equation of Bx equal to 0 by 1 by C. Then I will also introduce another invertible matrix C. So, that will be some form, it will be again 1 0 0 0 1 by C 0 0 0 1. So, E2 we will see that E2 into E1 into A equal to basically A please. So, each I have shown it for the multiplication by constant term non-zero constant, but it can be also shown for any other two operations what I have introduced here. For that also you will get elementary matrices please, which are invertible please. So, when you are doing some elementary row operations using these three basic elementary operations, one may have new systems. So, now using couple of elementary row operations, one can have a new system say B star, where this B star x is a new system obtained from my suppose given system Ax equal to 0. Then we see that both these systems are equivalent. But before that let me introduce one more terminology called equivalent matrix please, equivalent matrices please. Two matrices A and B order m cross n are said to be equivalent provided one can be obtained from other by considering finite number of elementary row operation, please, row operations. So, the way we used to get equivalent matrices, from this we can also talk about the solution of the system Ax equal to 0 and Bx equal to 0 when A and B are equivalent matrix also. So, it is like this is small, we can say theorems. Let A and B be two M cross N matrices over the field capital F and are also row equivalent. Then the system Ax equal to 0 and Bx equal to 0 have same solutions, have the same solutions. See, the proof is very straightforward, it can be done like this. Let B can be obtained from A by a finite number of elementary row operations. A goes to say A1, then goes to A2. When I am doing this elementary operation is, then I am finally suppose at the AK which is equal to B. So, if I say that the two matrices A and B are row equivalents, means I can obtain one from others by finite number of elementary operations. Let me consider A can be obtained from B by exactly one elementary operations. Then I will have again, suppose we have done for that one, that system Ax equal to 0 and Bx equal to 0 have same solutions. Then again applying B one more elementary operation, I will have another new systems, and then again I will show that B and suppose D they have the same solution space. So, I will basically give the proof for this results considering that B can be obtained from A by a single elementary operations. Let us consider B can be obtained from A by one elementary row operations, 3 row operations. So, when I am doing the elementary row operation, that may be elementary operation 1, it may be elementary row operation 2 or elementary row operation 3, the way I have defined. I mean multiplying by constant to some row, or maybe exchanging some row by multiplying another row to constant plus adding to it, or exchanging the rows also. So, I have taken only one elementary operation has been used for A and obtain B please. So, while doing these things, we have obtained the system Bx equal to 0, where each equation is linear combination of equations of Ax equal to 0. So, this implies the system Ax equal to 0 and Bx equal to 0 are equivalent. They have same solutions please. So, if I consider two matrices which are equivalent, row equivalent to each others, then their corresponding system Ax equal to 0 and the system Bx equal to 0 also have the same solution please. Since our objective is to answer the questions which what we have raised, that how to check whether system has solution or not, or and if the solution exists, how to find the solutions. So, we have to basically follow a particular path through which we can take the help of computer and answer our question please. So, in these directions, let me introduce one terminology, it is called row reduced matrix please, row reduced matrix. An M cross N matrix capital A defined over a field capital F is said to be a row reduced matrix provided first conditions, the first non-zero entry of each non-zero row must be equal to 1. Second, any column containing the so let me also add one more thing in the first conditions. This entry is also called as leading entry please, leading entry. So, leading entry for that corresponding row please. Any column containing the leading entry of some non-zero row, then all other entries of that column are 0. So, for example, if I consider A equal to 0 matrix, say 0 0 0 0, Can I say that it is a row reduced matrix? Certainly answer is yes. Why? Does it satisfy condition 1 or condition 2? Answer is again yes. Condition 1 says that the first non-zero entry of each non-zero row. Since there is no non-zero rows, so there is no question of the first condition please. And since there is no leading entry, so therefore second criteria is also by default satisfied. So it is a row reduced matrix. Let me consider another one. Say our trivial identity matrix, say 1 0 0 0 0 0 0 1 0 and 0 0 0 1 please. Does it satisfy again the criteria 1 and 2? Answer is yes, because first non-zero entry of first row is 1 and all the entry of the first column which contain the leading entry of the first row are 0 also, and it is also valid for the second column which contain the leading entry of the second row, and similarly for the third column and fourth column. So, it satisfied all the required criteria of the definition of row reduced matrix space. But these are all trivial examples. This is example 2. Let me take some non-trivial example. Let me take say B is equal to something like this 0 0 0 0 1 and 0 1 0 0 0. Let me take 0 1 and 0 0 0 0 0 0 0 0 0 0 0 0 0. Now again you see this is a 6 cross 5 matrix, and I see the first row is also non-zero, and the first non-zero entry is 1 which is appearing in the fifth column, and fifth column all other entries are 0. Then second row which is also non-zero and the leading entry appearing in second columns and all other entries in that corresponding column are 0 also. Similarly for the third row leading entry appear in the third columns and all other entries 0. So it is satisfied 1 as well as 2 please. So B is also a row reduced matrix space. So B is also a row reduced matrix. Now the question is it possible that if one picked up any m cross n matrix defined over the field say capital F, one can also have corresponding a row reduced matrix? Answer is yes. So this is small results in terms of theorem. Each m cross n matrix A is row equivalent to a row reduced matrix R. Again m cross n matrix, m cross n row reduced matrix R please. How to prove it? Given matrices A is your A11 to A1n and then A m1 to A mn, this matrix please. To check whether the first row is a non-zero row or not, whether first row of A is a non-zero row or not. If it is 0 row, then condition 1 of the definition of row reduced matrix is satisfied by default, is satisfied. Else, let the first entry, first non-zero entry of the first row appear in kth column. Then divide first row by A1 k, or that is multiplying 1 upon A1 k to the first row, it will give my, then the condition 1 will be satisfied, because the first non-zero entry will be 1. So, condition 1 is satisfied. To satisfy the corresponding condition 2, if the leading entry appear in the kth column, all other entry has to be equal to 0, then add minus A I k times first row to all rows I equal to 2 to m. So that condition 2 will be also satisfied. So, satisfied. Go to second row. Again, if second row is 0 rows, then nothing has to be done, else find out the first non-zero entry of the second row and then divide that corresponding number to the second row, so that leading entry will be equal to 1 place. Add third row, fourth row and all other rows by multiplying second row by corresponding number k, suppose is k1, suppose leading entry appear in k1 column, say then A I k1, I will basically from your 3 to m. So that again second condition will be satisfied, please. Okay. And if one do it like this way, certainly after a finite step we will come to the row reduced matrix form, please. If second row is a 0 row, then nothing has to be done, nothing has to be done for this row, else find out the first non-zero entry of this row. Let it appear in k1 column, then divide second row by A 2 K 1 please. So, the first criteria will be again satisfied. Now, also at minus A I times K, I have given the name K 1, right, A I K 1, first at minus A I K times second row to all rows for I equal to 3 to m. Second criteria will be also satisfied. Right. Continue in this way. After a finite step, one will get corresponding row reduced matrix R. So, for each m cross n matrix, one can have a corresponding row reduced matrix also. Again similarly, I can say that the system Ax equal to 0 and Rx equal to 0, where R is row reduced matrix, the matrix of A have same solution please, have same solution please. Since so A and R are row equivalent, because R is obtained from A by finite number of elementary row operations. So, therefore, A and R are row equivalent. As a result, the system Ax equal to 0 and Rx equal to 0 have the same solution please. So, we have seen that for any m cross n matrix A, one can have corresponding a row reduced matrix R, and the corresponding system Ax equal to 0 as well as Rx equal to 0, they have same solutions please. Thank you.